We remember Titanic wrong. For over a century, the world has remembered April 15, 1912, as the night a love story ended in tragedy. We remember a grand staircase, a string quartet playing as water rose around them, and two fictional passengers clinging to a piece of debris in the North Atlantic. We remember romance. We remember fate. We remember the ship that couldn't sink. But Titanic was not a love story. It was a systems failure. The largest moving object ever built by human hands didn't sink because of destiny or divine punishment. It sank because of decisions, calculated risks, economic pressures, regulatory gaps, material limitations, and a series of small compromises that accumulated into catastrophe. Every choice made in the 2 years before that ship left Southampton carried weight. Every message ignored, every warning dismissed, every design alteration made for aesthetics or profit rather than safety. All of it mattered. This is not the story of Jack and Rose. This is the story of how engineering ambition, corporate priorities, and human overconfidence converged on a single point in the North Atlantic. This is about why the ship actually sank, and what we've spent the last century trying not to see. The question is not, could Titanic have been saved? The question is, why wasn't it? In 1907, the White Star Line faced a problem. Their competitors were building faster ships, vessels that could cross the Atlantic in record time, capturing the lucrative passenger market and the prestige that came with speed. White Star's chairman, J. Bruce Ismay, decided on a different strategy. They would not compete on speed. They would compete on size, on luxury, on the promise of absolute safety. The plan was ambitious. 3 sister ships, each larger than anything afloat. The Olympic-class vessels would redefine ocean travel. Olympic would launch first in 1910. Titanic would follow in 1912. Britannic would complete the trio in 1914. Together, they would dominate the Atlantic. These ships were extraordinary engineering achievements. Titanic measured over 882 feet long and displaced 52,000 tons. It had a double bottom, a second hull beneath the main hull, designed to protect against underwater collisions. It had 16 watertight compartments running along its length, separated by bulkheads equipped with remotely controlled doors. If the ship struck something, the affected compartments could be sealed off, isolating the damage. This is where the word unsinkable entered the story. But we need to be precise about what that word meant. The term was never an absolute guarantee. It appeared in technical journals and promotional materials as a qualified statement. The ship was designed to remain afloat, with any 2 compartments flooded, or even with the first 4 compartments breached. By the standards of 1912 naval architecture, this was extraordinary. Most ships would founder if a single compartment filled with water. Titanic could theoretically survive damage that would sink nearly any other vessel. But unsinkable became mythology. The public heard certainty where engineers had offered probability. And within that gap, between engineering reality and public perception, disaster was already taking shape. The first compromise was subtle, almost invisible. The watertight compartments that ran along Titanic's length did not extend all the way to the top deck. They rose only as high as E-deck, about 15 feet above the waterline. This was not an oversight. It was a deliberate design choice. Extending the bulkheads higher would have created problems. Passengers and crew needed to move through the ship. Doorways, corridors, and staircases had to connect different sections. Sealing the compartments completely would have made the vessel difficult to operate. So the bulkhead stopped at E-deck, leaving the tops of the compartments open. The calculation was simple. Under normal circumstances, even with 4 compartments flooded, the ship would list but remain afloat. The water would not rise high enough to spill over the bulkheads into adjacent compartments. The math worked as long as the damage remained within predicted parameters. But there was a problem the designers did not fully account for. If the bow section of the ship dipped low enough, if the weight of water in the forward compartments pulled the nose down, the flooding would not stay contained. Water would reach the top of the first bulkhead, spill over into the next compartment, pull the bow down further, and repeat. A cascade, a chain reaction. The watertight compartments would become a conveyor system, moving water from bow to stern until the entire vessel sank. This failure mode was theoretically possible, but it seemed unlikely. It would require damage extensive enough to flood at least 5 compartments. And what kind of collision could breach 5 compartments at once? The designers made another choice. One that had nothing to do with engineering and everything to do with appearance. Titanic's grand staircase was a masterpiece of Edwardian design. It descended through 6 decks, an open shaft of carved wood and wrought iron that allowed natural light to flood the first-class areas. It was breathtaking. It was also a structural liability. That open staircase created a vertical channel running through the ship's core. In the event of flooding, water would not remain confined to lower decks. It would rise through that open shaft, spreading rapidly upward. Watertight compartments mean nothing if water can bypass them through vertical passages. But the staircase was not designed for safety. It was designed for spectacle. First-class passengers paying premium fares expected grandeur. White Star delivered. The engineering risk was accepted as the cost of marketability. Then there were the lifeboats. Titanic carried 20 lifeboats, with a total capacity of 1,178 people. The ship could carry over 3,500 passengers and crew. The math was obvious. There were not enough lifeboats. But this was not an oversight. It was entirely legal. British maritime regulations in 1912 were based on ship tonnage, not passenger capacity. A ship of Titanic's size was required to carry 16 lifeboats. White Star exceeded that requirement by adding 4 collapsible boats. By law, they were compliant. By logic, they were catastrophically underprepared. Early designs for Titanic included davits capable of handling up to 64 lifeboats. But davits take up space. More lifeboats would clutter the promenade decks, obstructing passengers' views of the ocean. They would also undermine the marketing message. If the ship was unsinkable, why would it need lifeboats? The decision was made. Fewer boats, more deck space, better aesthetics. The regulations allowed it, so no change was made. Risk was not eliminated. It was simply pushed out of view. Shipbuilding in 1912 relied on 2 materials to hold the hull together: steel and iron. Steel plates formed the ship's skin. Rivets held those plates to the frame. 3 million rivets, driven by hand, connected Titanic's structure. But not all rivets were the same. The highest stress areas, the midsection of the hull, used steel rivets. Steel is strong and ductile. It bends before breaking, but steel rivets required hydraulic machines to install, and those machines could not reach the curved sections at the bow and stern. In those areas, workers used iron rivets, driven manually with hammers. Iron is cheaper than steel. It's easier to work with, but it's also more brittle, especially in cold water. At temperatures near freezing, iron loses ductility. It becomes prone to fracture. Strike it hard enough, and it shatters rather than bends. Metallurgical analysis of recovered Titanic rivets has revealed high slag content, impurities, left over from the smelting process. This weakened the rivets further. When the ship struck the iceberg, the iron rivets along the starboard bow didn't just bend, they failed, they popped. The hull plates separated along the seams, opening a series of narrow gaps that allowed water to pour in. This is called a zipper effect. Once the first rivet fails, stress concentrates on the adjacent rivets. They fail in sequence, propagating the damage along the seam. The iceberg itself did not tear a massive gash in Titanic's side, as popular imagination suggests. It created a series of small ruptures along rivet lines. enough to flood 6 compartments, more than the ship could survive. If steel rivets had been used throughout the bow, the outcome might have been different. The hull might have dented, but remained sealed. The compartments might not have flooded, but steel was expensive and the curved sections of the hull required manual labor. The decision to use iron rivets in those critical areas saved money and time. It also doomed the ship. The iceberg that Titanic struck was not unusual. It was not a rogue anomaly or a once-in-a-century phenomenon. It was an ordinary piece of glacial ice, calved from a Greenland glacier years earlier, drifting south with the Labrador Current. Icebergs form when chunks of glaciers break off and enter the ocean. Most remain in Arctic waters, melting slowly in the cold northern seas, but some drift south, carried by ocean currents into the North Atlantic shipping lanes. Every year, hundreds of icebergs make this journey. Most pass unnoticed, posing little threat to shipping because vessels see them in time to maneuver. But 1912 was unusual. That winter was mild, which meant more icebergs calved from Greenland glaciers. By April, an abnormally high number had drifted into the transatlantic routes. Ships reported ice warnings daily. Titanic received multiple messages about ice fields ahead. The crew knew the danger was present. The iceberg itself was unremarkable in size. Estimates suggest it rose about 50 to 100 feet above the waterline, with perhaps 90% of its mass submerged, as is typical. It was not hidden, it was not invisible. Under normal conditions, a lookout should have spotted it from over a mile away, giving the ship several minutes to alter course. But the conditions that night were anything but normal. April 14th, 1912 was a moonless night. The Atlantic was calm, no wind, no waves. Under ordinary circumstances, calm seas are a blessing for ocean travel. Passengers experienced less motion sickness. The ship moved smoothly. But calm water also eliminates one of a lookout's most reliable tools: the visual detection of waves breaking against objects. When waves strike an iceberg, they create foam and spray, visible even in darkness. But that night, the ocean was flat. There were no waves. The iceberg sat in water as smooth as glass, its base indistinguishable from the surrounding sea. The air temperature was also critical. The water was near freezing, but the air above was slightly warmer. This temperature differential created a phenomenon called a superior mirage, a form of atmospheric refraction where light bends as it passes through layers of air at different temperatures. To an observer on Titanic's deck, this mirage would have created a false horizon, making distant objects appear lower or obscured. The iceberg, already difficult to see in the darkness and calm water, would have been further masked by atmospheric distortion. By the time the lookouts spotted it, the distance had closed to less than 500 yards. At Titanic's speed, 22 knots near full velocity, 500 yards translated to roughly 37 seconds. That was the window. 37 seconds to process the sighting, relay the warning to the bridge, and execute a maneuver. Communication failures began. Long before the iceberg was sighted, Titanic's Marconi wireless operators spent the voyage transmitting passenger messages, personal telegrams from wealthy travelers, to business contacts and family ashore. These messages were profitable. Each one generated revenue. The operators were employed by the Marconi Company, not by White Star Line, and their incentive was to process as many paid messages as possible. Ice warnings from other ships were not paid messages. They were courtesy transmissions, interrupting the flow of commercial traffic. Throughout April 14th, Titanic received at least 6 warnings about ice in the ship's projected path. Some were delivered to the bridge, others were not. The final warning, sent by the nearby SS Californian at 11 p.m., was cut off by Titanic's senior operator, who was busy with passenger backlog. The message never reached the bridge. This was not sabotage. It was prioritization. The wireless system was new technology, and protocols for maritime safety communication were informal. No regulation required operators to prioritize ice warnings over commercial traffic. The operators did their job as they understood it, but the information that might have altered Titanic's course, detailed coordinates of ice fields directly ahead, remained undelivered. The SS Californian presents another layer of complexity. Californian had stopped for the night, surrounded by ice roughly 10 to 20 miles from Titanic's position. Its wireless operator had gone off duty at 11:30 p.m., standard practice for ships with a single operator. When Titanic struck the iceberg at 11:40 p.m. and began sending distress signals, Californian's wireless was silent, but Californian's crew saw something. Officers on watch observed lights in the distance. A ship apparently stopped. They saw what they described as rockets being fired into the sky. Titanic was indeed firing distress rockets, white flares bursting above the ship at intervals, the recognized signal for a vessel in mortal danger. Californian's crew did not interpret the rockets as distress signals. They assumed the ship was communicating with another vessel, perhaps signaling its position. They did not wake the wireless operator. They did not attempt to investigate. This was not malice. It was a failure of recognition, compounded by the limitations of visual communication across dark water. Could Californian have reached Titanic in time to make a difference? The distance, the ice fields, and the time required to maneuver make this uncertain, but the question itself reveals the problem. Information existed that could have changed the outcome. It was seen, received, and then not acted upon. At 11:39 p.m., lookout Frederick Fleet spotted the iceberg directly ahead. He struck the warning bell 3 times and telephoned the bridge. 6 seconds later, First Officer William Murdoch received the message. He ordered the helm hard to starboard, a command that, under the steering conventions of the time, would turn the ship to port, to the left, attempting to pass the iceberg on its port side. Simultaneously, he ordered the engines reversed. This was standard collision avoidance procedure. When an obstacle appears ahead, you turn and you slow down. The logic is intuitive, but in this case, it was exactly the wrong choice. Reversing the engines killed the ship's maneuverability. Titanic's rudder was effective only when water flowed past it with sufficient force. Thrust from the propellers provided that flow. When the engines reversed, the water flow slowed and the rudder lost effectiveness. The ship's turning rate decreased just when it needed maximum agility. At the same time, the turn itself exposed Titanic's side to the iceberg. A head-on collision would have crumpled the bow, flooding perhaps the first 2 or 3 compartments. The ship would have survived. Passengers in the forward sections might have been injured, but the vessel would have remained afloat, limping back to port for repairs. But Murdoch turned. The iceberg scraped along the starboard side, its submerged spur punching and tearing at the hull below the waterline. The contact lasted less than 10 seconds, but the damage extended across nearly 300 feet of the ship's length. 6 compartments breached, 6 compartments flooding. Titanic could survive 4. It could not survive 6. The physics are straightforward. Each flooded compartment added thousands of tons of water weight to the bow. The ship's buoyancy depended on displacing water with air-filled volume. As compartments filled, that volume disappeared. The bow sank lower, the stern rose higher, and because the watertight bulkheads only extended to E-deck, the water spilled over, cascading from one compartment to the next. The ship was designed with the assumption that localized damage would remain localized, but this damage was not localized. It was distributed, sequential, and self-propagating. Once the cascade began, no pumps, no countermeasures, no human intervention could stop it. By midnight, 15 minutes after impact, water had flooded the first 5 compartments and was beginning to overflow into the 6th. The ship's designer, Thomas Andrews, was summoned to assess the damage. He performed rapid calculations based on reports from crew inspecting the lower decks. His conclusion was absolute. Titanic had perhaps 90 minutes, at most 2 hours, before it sank. There were over 2,000 people on board. There was lifeboat capacity for fewer than 1,200, and the nearest ship capable of reaching them in time, the RMS Carpathia, was 58 miles away. The mathematics of survival had become unforgiving. The evacuation of Titanic was chaotic, confused, and tragically inefficient. Lifeboats designed to hold 65 people were launched half-empty. The first boat to leave carried only 28 occupants. Over the next 2 hours, boats departed with an average occupancy of roughly 60%. In total, the lifeboat saved approximately 700 people. They had capacity for nearly 1,200. 400 potential survivors were lost to poor loading decisions. Why were the boats underfilled? Several factors converged. First, passengers did not believe the ship was sinking. Many refused to board lifeboats, convinced they were safer on the massive, brightly lit vessel than in small wooden boats on a freezing ocean. Crew members did not convey the severity of the situation, partly because they did not fully grasp it themselves, and partly because creating panic seemed more dangerous than maintaining calm. Second, the crew was unfamiliar with the lifeboat equipment. White Star had not conducted a full lifeboat drill before departure. Officers were uncertain about the boat's capacity and structural limits. Some believed the davits could not support fully loaded boats and deliberately limited the number of passengers boarding, planning to pick up more people from the water after launch, a plan that proved impossible to execute. Third, the directive, "Women and children first," was interpreted inconsistently. On the port side, Second Officer Charles Lightoller enforced it rigidly, barring men from boarding even when seats remained empty. On the starboard side, First Officer Murdoch allowed men to board if no women were nearby. This inconsistency was not coordinated policy. It was individual judgment under pressure, made in darkness, with no communication between officers on opposite sides of the ship. Class disparities were real but often misunderstood. First-class passengers had closer access to the boat deck and received earlier warnings to don life jackets. Third-class passengers housed in the lower decks faced locked gates and confusing corridors as they tried to reach the upper levels. Some gates were locked to comply with immigration regulations, designed to prevent third-class passengers from entering first-class areas, not to trap them. But in an emergency, those barriers became lethal obstacles. Survival statistics reflect these disparities starkly. Of the approximately 325 first-class passengers, around 60% survived. Of the 285 second-class passengers, about 42% survived. Of the 706 third-class passengers, only around 25% survived. Wealth and proximity to the boat deck correlated directly with survival probability. But the greatest loss of life was among the crew. More than 600 crew members perished, not because they were denied lifeboat access, but because they remained at their posts. Engineers stayed below decks, maintaining power and pumps as long as possible, knowing they had no chance of reaching the lifeboats in time. Wireless operators transmitted distress signals until seawater shorted their equipment. Stewards guided passengers upward, then found no boats left for themselves. By 2:05 a.m., the last lifeboat had departed. Over 1,500 people remained on board. The bow was submerged. The stern was rising out of the water at an increasingly steep angle. The ship's structure, never designed to support its own weight out of water, began to fail. Rivets popped, steel plates buckled, and at 2:20 a.m., Titanic's hull snapped in two. The bow section sank immediately. The stern, momentarily buoyant, rose nearly vertical before sliding beneath the surface. The water temperature was 28 degrees Fahrenheit, below the freezing point of fresh water, but above the freezing point of seawater due to its salinity. At that temperature, a human body can survive perhaps 15 to 30 minutes before hypothermia causes unconsciousness and death. Most of those who went into the water died within 20 minutes. Lifeboats, floating nearby with empty seats, did not return to pick up survivors. Passengers in the boats feared being swamped by desperate swimmers. Only one boat, Lifeboat 14, commanded by 5th Officer Harold Lowe, returned to the wreck site. By the time it arrived, nearly everyone in the water was dead. Lowe's crew pulled 4 people from the water. 3 survived. RMS Carpathia arrived at 4 a.m., nearly 2 hours after Titanic disappeared. Carpathia's captain, Arthur Rostron, had pushed his ship beyond its rated speed, risking his own vessel to reach the distress position as quickly as possible. But he arrived to find only lifeboats, floating wreckage, and over 1,500 bodies, beginning their slow descent to the ocean floor, 2.5 miles below. The investigations began immediately. The British Board of Trade convened an inquiry. The United States Senate launched its own. Both sought answers to the same questions. Who was responsible? What decisions led to disaster? Could it have been prevented? The findings were damning and complex. Captain Edward Smith was criticized for maintaining speed despite ice warnings, though his decisions reflected standard practice at the time. Ships routinely traveled at full speed until ice was sighted, then reduced speed. The White Star Line was faulted for insufficient lifeboats, though they had exceeded legal requirements. The ship's design was scrutinized, revealing the vulnerabilities in the watertight compartment system. But the inquiries also revealed something deeper. Titanic was not an isolated failure. It was a symptom of systemic problems in maritime regulation, corporate oversight, and engineering practice. Ships were built to regulations designed for smaller vessels in an earlier era. Wireless communication lacked standardized safety protocols. Lifeboat requirements had not kept pace with ship size. Training and emergency procedures were inconsistent. The changes came swiftly. Within months, international agreements mandated that ships carry enough lifeboats for every person aboard. Lifeboat drills became mandatory. Wireless operations were required to maintain 24-hour watch on distress frequencies. The International Ice Patrol was established, tasked with monitoring iceberg movements in the North Atlantic and broadcasting warnings to all vessels. That organization still operates today, and no ship following its guidance has struck an iceberg since its inception. Material standards evolved. The use of brittle iron rivets was phased out in favor of steel throughout hull construction. Bulkhead designs were revised, with requirements for compartments to extend higher and include more robust sealing mechanisms. Engineering societies developed new standards for ship stability and damage control. Titanic became a reference case, studied in engineering schools, cited in regulatory debates, analyzed in safety courses. The ship sinking did not result from a single catastrophic flaw. It resulted from accumulated vulnerabilities, small compromises, acceptable risks, and decisions that seemed reasonable in isolation, but proved catastrophic in combination. This is the nature of systemic failure. No single point of failure dooms the system. Instead, multiple small failures align, each one insufficient alone, but together creating a pathway to disaster. Engineers call this the Swiss cheese model. Each layer of defense has holes, and catastrophe occurs when those holes align, allowing a failure to pass through every barrier. We return to the question posed at the beginning. Why did Titanic sink? The iceberg was a trigger, not a cause. The ship sank because watertight compartments were not tall enough, because iron rivets were used in critical areas, because lifeboats were treated as a regulatory formality rather than a survival necessity, because ice warnings were not prioritized, because wireless operators were incentivized to process commercial messages over safety transmissions, because officers made a split-second decision to turn rather than collide head-on, because evacuation procedures were improvised in darkness and confusion. Each of these factors alone would not have sunk the ship. Together, they were lethal. This is the lesson Titanic teaches, and it extends far beyond maritime engineering. Every complex system, whether a ship, a spacecraft, a financial market, or a public health infrastructure, contains vulnerabilities. Those vulnerabilities remain hidden until conditions align to expose them. The challenge is not to eliminate all risk, which is impossible, but to recognize where small compromises accumulate into systemic fragility. Progress in engineering is often written in disaster. We learn what not to do by witnessing the consequences of what we did. The regulations that followed Titanic have saved countless lives over the past century. The International Ice Patrol has tracked over 20,000 icebergs, preventing collisions that might have replicated Titanic's fate. Modern ships have redundant bulkheads, sufficient lifeboats, continuous distress monitoring, and materials tested for cold water brittleness. But the fundamental dynamic remains. Every ship, every aircraft, every structure we build represents a negotiation between safety and cost, between redundancy and efficiency, between caution and confidence. Engineers calculate risk. Managers weigh priorities. Regulators set thresholds. And sometimes those calculations prove insufficient. Titanic was not the victim of fate. It was the product of decisions. Decisions made in boardrooms and shipyards, on drawing boards and balance sheets. Decisions to accept risk, to prioritize appearance over function, to follow regulations rather than exceed them. Decisions made by people who believed they had built something unsinkable because the idea of failure was too uncomfortable to fully consider. Technology does not fail alone. It fails because human beings design, operate, and manage it, and human beings are fallible, subject to pressures and incentives that do not always align with safety. We build systems to mitigate that fallibility, but the systems themselves are built by humans, and so they inherit our limitations. Titanic sank because we believed it couldn't. That belief shaped every decision that made the sinking possible. And that is the most dangerous vulnerability of all, the assumption that we have eliminated risk when we have only hidden it from view. The ship lies now on the ocean floor, 2.5 miles down, slowly disintegrating in the cold and pressure. In another century, it will be unrecognizable, reduced to rust and memory. But the lessons it carries remain. We remember Titanic wrong, but we must remember it, not as romance, not as tragedy, not as the ship that couldn't sink. We must remember it as the ship that did sink and understand why. Because every system we build today contains the same vulnerabilities, the same compromises, the same risks we choose not to see. Until conditions align, until the holes in the Swiss cheese line up, until 37 seconds is all the time we have left and it is not enough. And then we learn again what hubris costs.